Hello everyone, I'm Paul and today we're solving problem 2040, kth smallest product of two sorted arrays. This one is hard and the key here is binary search. So let's see how to solve this step by step. We're given two arrays, nums1, nums2 and an integer k. So let's say we get this and our job here is to return the kth smallest product. So we will get all the products of these arrays and we need to return the kth smallest. 2 times 3 is 6, 2 times 4 is 8, 5 times 3 is 15 and 5 times 4 is 20. And now we need to check what is the second smallest product here. It's 8, so we return 8. Now here we have the constraints and we know that every number can be up to 10 to the power 5. This means we can't iterate this and this in a nested loop to build this and then just return the kth smallest product. That will throw a TLE, time limit exceeded, so we need to think about something more efficient. And here we have sort of like a hint, which is that nums1 and nums2 are sorted. So we can use binary search here. Let's see how. Now let's say we have the same input and we run a binary search from the smallest possible product, meaning 10 to the power 5 times 10 to the power 5 negative. We can have negative values here. And the right bound will be 10 to the power 5 times 10 to the power 5 positive. So the mid pointer is initially in between these two, meaning 0. And now this will be our target product or the target. We'll call this target product or TP. This is initially 0. And now we need to check how many products do we have here that are smaller or equal to this target product. And remember, we can't iterate this and this in a nested loop because that will require an n times m complexity, which will throw a TLE error. So we need to think about something more efficient. And luckily for us, there's something we can implement here that runs in big O of n log m. So let's see how this works. We know that to get the target product, we need to take one number from n1 and multiply this with one number from n2. So let's say we have this and we have this. We can clear this, and to get n2, the optimal n2 to get this target product, we will need to do TP divided by n1. So we can run a binary search here with this value to get the amount of products that are smaller or equal to this target product. We iterate this from left to right with an I pointer from index 0. So first we have a 2. We know our target product is 0. So n2 in this case is 0 divided by 2. And this is 0. So now we'll run a binary search with this target on this array. So this would be something like this. Left pointer is here at index 0, right pointer is here at index 1. And the mid pointer is here at index 0 also. 3 is greater than 0, so we need to move the mid pointer to the left. And to do this in binary search, we move the right pointer to mid minus 1. So we move the right pointer here. And now right is smaller than left, so we end the binary search here. We return this left, which is 0. This is index 0, this is index 1. So we return this. So we will have a variable we will call this count, in which we will keep track of how many products do we have that are smaller or equal to this target product. So when the I pointer is here at index 0, when we have a 2, we have 0 products that are smaller or equal to this target product. So we add a 0 here, meaning we keep this 0. Now we update the I-pointer, we are here. So now we are looking for 0 divided by 5. So we are looking for 0 here. So we run a binary search again here, and the result for this binary search will be 0. So we add 0 to the count, and the count is still 0. So now we update the I-pointer and we reach the end. And what this means is we have 0 products that are smaller or equal to our target product. And given that the result for this was 0, and 0 is smaller than k, we need to move our target product to the right. We need to increment this value. And the way to increment this value is move the left pointer to mid plus 1 in this case. So now the left pointer will be here at mid plus 1, meaning at 1, and the midpoint will be somewhere here. So the value for this midpoint is something like 5, 0, 0, 0, 0, and more zeros. So now we will do the same. We will take this as the target product and we will check how many products do we have here that are smaller or equal to this target product. So remember, we iterate this from left to right from index 0, and every time our N2 target will be this value divided by each of these, in this case 2, and we are running a binary search with this value here, and this is a very big number, so the binary search here in this case will be definitely here. So we will add to the count 2. Next we iterate the next element, meaning we move the I-pointer here. Now the I-pointer is here, so we are looking for this value, 5 and many zeros divided by 5. And this is also a very big number, so the result of this binary search will be here, meaning we need to add 2 to the count, so the count is 4. Now we update I, we reach the end, and the result is 4. So 4 is greater than 2, which is k. And what this means is with this target we have 4 products in these 2 arrays that are smaller or equal to this target product. So we can move this midpoint to the left, and to do this we move the right pointer to the mid. So now the right pointer will be somewhere here and the mid pointer will be in between, and this will keep going. This number is 25 and something, so next the right pointer will be here because this number is still very big, the mid pointer will be here, and this will continue. And at some point we will be here. So now the target product is 19, and now we iterate this from left to right. We start with 2, and now we are looking for 19 divided by 2. So we are looking for 9 because we round down this value for now. So we run a binary search to see where do we put this 9 in nums2, and we put the 9 here. This is index 0, this is index 1, this is index 2. So the binary search for this will be 2. So we add to the count, in this case 2. Now the I-pointer is here and our target is 19 divided by 5. This is roughly 3, and we need to do a binary search here with this 3, and the 3 will be here. This means the binary search will return 1, so we add this 1 to the count, which is now 3, and 3 is greater than k, and this means we need to move this value to the left. So we move the right pointer to the mid pointer. Now the midpoint is here and the target product is 10, and we iterate this from left to right. So now we are looking for 10 divided by 2. So we are looking for 5. And if we run a binary search with 5 here, we will get this, meaning 2. So we add to the count 2, we update I, we're here, and now our target is 10 divided by 5. So the target is 2. And if we run a binary search with 2 here, we will get this, meaning 0. So we add 0 to the count, and now the count is equal to k. So we need to reduce this even more, and now the target is 5. So our target product is 5. We iterate this from left to right. Now we are looking for 5 divided by 2. We round down this is 2. So we are looking for 2 here with a binary search, and the result will be 0. So the count is currently 0, and we update I. Now we have 5, and we are looking for 5 divided by 5, meaning we are looking for 1. So we run a binary search with this here, and the result is also 0, so we add 0 to the count, we update I, we reach the end, and we get this. Now this is smaller than k, so we need to move the midpoint to the right, meaning we move the left pointer to mid plus 1 here. So now left is 6, right is still 10, and the midpoint is 8. So our target product is 8, the count is 0. Now we're here with the I pointer, and we are looking for 8 divided by 2. So we are looking for 4 here. And if we run a binary search with 4 here, we will get this, meaning 2. So we add 2 to the count, we update I. Now we're here, and we are looking for 8 divided by 5, meaning 1. Remember, for now we are rounding down this. And if we run a binary search with 1 here, we get this, meaning we need to add 0 to the count. Next we update I, we reach the end, and we get this. This equals to k, so we can move this to the left, meaning we move right. Now left is 6, mid is 7, right is 8. So finally the midpoint is here, so the target product is 7. And we start with the 2, so now we are looking for 7 divided by 2, which is 3. We are looking for this here, and this will return 1. So we add to the count 1. Now the I pointer is here, and we are looking for 7 divided by 5 here. This is 1. So this will return 0, meaning we need to add 0 here. We update I, we reach the end, and 1 is smaller than k. So now we need to move mid to the right, meaning we move the left pointer to mid plus 1. So now the left pointer is here. Now left equals right, meaning we can return left or right, meaning 8. So the final result in this case is 8. So 8 is the kth smallest product that we can get from this. Now the time complexity for this entire approach will be big O of log range, and this is the maximum range that we can get among all the possible values, meaning this goes from negative 10 to the power of 5 times 10 to the power of 5 up to 10 to the power of 5 square, and this is times n, meaning the size of nums1, log m, meaning the size of nums2. Remember, we are running binary search here also, that's why this is log m. And space complexity will be big O of 1. So this is it for the approach. I know this is tricky. This is a hard binary search problem, but if you didn't get the idea, maybe you can watch this video again. And here we'll go with the code, and hopefully you will get the idea. First, m equals length of nums2. And now we'll create our function product to get the amount of products that are smaller or equal to some target. And the count for this will be 0 initially, and we will return the count. And now we need to iterate nums1, so for n1 in nums1. And here it's something that I didn't say before, and it's that if we get a negative value, we need to reverse the result for the binary search. Because remember, we're trying to get the amount of products that are smaller or equal to some target. And this means that if the value for n1 is negative, we need to take every element that's not included in the binary search. Let's see how can we do this. First, we have the case in which n1 is positive, which is what we saw before. So if n1 is greater than 0, count plus equal, and in Python we can do a binary search like this, bisect right, and this is actually very efficient in Python. And we'll do this binary search on nums2, and our target will be target divided by n1. Remember, we need to round down this. And now, else if n1 is smaller than 0, in this case we need to reverse the result. So count plus equal m minus bisect, and instead of right we'll use bisect left in this case, because otherwise we'll go off by 1. So bisect left, and this binary search is also on nums2, and target divided by n1. Remember, here we round down this value, but here we need to round up the value. So here we use ceil, else if n1 equals 0 and target is greater or equal to 0, we add to the count the amount of elements in the nums2 array. Now it's very common to go off by 1 in these binary search problems, especially in this one, which is very hard, and here we have nested binary searches. So I recommend you to try this on your own and try and get the right result. This is a great exercise for the brain. Here, this is one good combination. This works, but I recommend you to try this on your own. Sometimes you need to round down or round up something. So try to think about this, be patient with your brain, and keep on trying. And now we are building the main binary search. So left, right are 10 to the power of 5 times 10 to the power of 5. And this is negative. This is the left bound, and the right bound is 10 to the power of 5 times 10 to the power of 5. And now, while left is smaller than right, mid will be left plus right minus low divided by 2. And if products mid is greater or equal to k, right equals mid, else left equals mid plus 1. And finally we return right. So this is it for the code. Now let's submit this and see if it works. As you can see, this works and it's very efficient. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.